So as we were back in the hydraulics lab just now, and we were leaving, Ethan made the observation that it wasn't just a single depth over that broad crested weir, that it was gradually getting shallower and shallower the closer you got to the end. And that's because the drop-off, the water's accelerating as it approaches that drop-off. And so we have gradually varying flow as it does that. So kind of the rule of thumb, or what I've observed in the lab, is that it's about a third the distance where we would see the critical depth. So there's a period where it's a little bit higher than the flow over the obstacle, where it's accelerating, and then it achieves critical, and then it's getting shallower and shallower as it approaches that drop-off. So, I mean, that was a good question, a good observation that, you know, we're saying the water flows at the critical depth over the obstruction, but there was multiple depths over the obstruction. It was a continuum of depths. And so how do you know which one of them to pick? Because one of the reasons of a broad crested weir is to measure the flow rate. So usually the way that they do that is they would, you know, have like a scale on the side of a flume, send the water through the flume and then see how deep is the water, or they have these ultrasonic sensors that acoustically are sending a signal down and measuring the depth of the water. But you'd have to calibrate a little bit to know what's the appropriate location to measure the depth in order to have the correct flow rate. So generally, like if it's a standardized design, there would be a certain point that you'd measure the flow depth at to use as the basis for determining the flow rate. Just to revisit some announcements which you've seen before, homework 11 is due on Monday before class, and then the design project final report is due on Friday the 25th. And so for that, it's where it's the final submission with the project. Everything should be polished perfectly. It's the sort of thing that you should consider as like a showpiece portfolio item, that if a prospective employer was asking to see an example of what you're capable of, the work that you're doing as an engineer, then this report is something where you could show them that, you know, you've got some critical thinking and logic skills with the demand estimation, that you've learned how to use with very minimal instruction a industry standard design software in the form of water gems, that you've done some reservoir sizing, that you can use spreadsheets for the calculations with reservoir sizing, that you can translate all that into a cost analysis. So, you know, this is a hypothetical design, but it exhibits some real world skills that you've developed. And so I think it's a good opportunity to make it look really nice, because it could be something that people besides just I look at. So if you have any questions related to the feedback I've given you on demand estimation or pipe sizing, let me know. I'm going to grade your reservoir sizing today and tomorrow, so you'll get that feedback, I think, with plenty of time to implement it all before the final due date. Any announcement related questions? All right, a couple of slides we didn't have time to look at in class previously, which is, I just noticed here that there we go, that'll sound better. Let me just make sure the microphone's working. All right. The length of a hydraulic jump is estimated a variety of different ways. This nomograph, which is made by the Bureau of Reclamation, which is a counterpart agency to the Army Corps of Engineers. I know a lot of people here are familiar with the Army Corps. The Bureau of Reclamation does a lot of the same work as the Army Corps. They mainly have their offices in the western part of the United States. But they've developed a lot of hydraulic figures that explains things like the performance of water coming off of a spillway, encountering a hydraulic jump. And the question is, how long will the jump be? And what this figure illustrates is, if you know the Froude number upstream prior to the jump, so that's here the horizontal axis, what you do is you'd go up and encounter where this figure is over to the left, and then it tells you the ratio of the jump length to the downstream depth. So from the Bellinger momentum equation, you would calculate y2, and then knowing the ratio of the jump length to y2, and where it comes on this figure, then you could find out how long the jump is. And so this is making the point that the length of the rollers, which is where you see like a lot of rapid like turbulence in the water and sometimes entrained air, those are the rollers. The hydraulic jump itself extends beyond the rollers a little bit further. And so this figure is meant to tell you the length of the jump before it reestablishes the normal depth downstream. So in general, the roller length relative to the jump length it's usually between 0.4, 40% of the length of the jump up to 70% of the jump length. So it varies. There's another equation that's been proposed, the Hager jump length equation, which you wouldn't have to use a figure for that. It uses a hyperbolic tangent, knowing the Froude number upstream prior to the jump, and then it gives you the length of the jump relative to the upstream depth rather than relative to the downstream depth. Our book even just talks about another jump equation without offering any attribution on who developed it or anything, but it's the simplest of all the methods. It's just saying that there's some coefficient between 5 and 6.9. You can multiply that by the change in depth and estimate the length of the jump from that. So there are some empirical ways of estimating how long the hydraulic jump will be, in addition to what the upstream and downstream depth is going to look like. Because we're pressed for time, we're going to skip over this example, but I'll email it to you just so you've got it available. I don't know if you have to use these jump length equations in the homework. Have you guys been working on the homework? You don't remember having to calculate the jump length. So I'll send you the example just so you'll have it as a reference, but I don't think you'll necessarily need to use it. All right, so the main event today is talking about underflow gates. And this is something I did a little bit when I was working professionally before I went and got my PhD. I lived in an area that had a lot of irrigation canals. And so we were working for the county agency that managed the irrigation water in the area. And I would have to figure out how big of a gate should be used and how high it should be opened to allow a certain amount of flow rate through. And an underflow gate could be just as simple as a metal plate with a bit of bent rebar welded to it, and it sits in a frame. It could be just as simple as that, where you're hoping for a little bit of friction in the frame to hold it in place when you lift it up. As the plate gets progressively heavier, then they have to put generally like a wheel or a motor on the frame to lift it up out of the water. And sometimes they get really big. You can see that this metal plate, I think that says it's 30 inches wide, 30 inches tall, and it's going to be very heavy and thick. So gates are used not just in irrigation situations, they're also used in wastewater treatment plants to allow water to flow from one point to another in the treatment plant. So it's important to understand how water behaves as it's flowing either under a gate or over a gate. There are gates like this which are designed to reduce the force required to lift the gate. And if we go back to these gates, you have to lift them partly because the metal plate itself is heavy, but also the pressure of the water on the gate is pressing it against the frame. And so there's going to be a lot of friction lifting it up because the hydrostatic force is acting over some area, and so there's a force inward on the gate that makes it difficult to raise as well. So a gate like this, if it's curved in shape, so you can kind of get a sense for its curved shape, and the forces act through a central axis. And so the hydrostatic pressure and the hydrostatic forces aren't adding to the force required to lift the gate if you have a central axis that all of the forces act through. It's just the weight of the gate that has to be lifted if you take this approach and have the curvature on it. So the energy equation, here we've got specific energy, as we were talking about back in the lab, the two terms being the depth and some representation of the velocity head. So if we're ignoring the energy losses, then we'll just say that the specific energy upstream is equal to the specific energy downstream. The reality is that there are some energy losses which we can't neglect if we want to maximize accuracy. And so there is an effect of continued acceleration after the water goes under the gate. And this vena contracta, which means that the flow is continuing to contract after it goes out from under the gate, can be described by here the coefficient of contraction, C sub C. You may remember that we talked about the C sub C when we did the orifice lab in fluid mechanics last semester, where the water was coming out from those little circular holes and the jet was going out. There was a coefficient of contraction there as well, where the jet diameter is actually smaller than the orifice diameter. So here, the coefficient of contraction is about 0.59 to 0.62, and so if the gate was open 1 meter, then that means that the flow depth after it continues accelerating would only be between 59 and 62% of that. So with gates, we can sometimes use the flow per unit width, so lowercase q can be calculated here, the capacity of the gate on a unit width basis, if we assume no energy loss, would be related to the upstream and the downstream depths. So assuming no energy loss doesn't really do us a lot of good because we are going to need to account for the energy loss for fluids that have viscosity like water. So gates like this are used to regulate the flow rather than quantify it. So we talked about broad-crested weirs. They don't do anything to regulate the flow in a dynamic way because it's a fixed object. It can't be easily taken in and put out. It's just there, and the purpose of the broad-crested weir is to quantify the flow. Gates, in contrast, we can use to regulate how much water is going what direction. Maybe we want to stop the flow of water to a certain canal when it's not their day to irrigate, so we'd use the gate to close off the path for the water. And the fact that it's underflow also is nice because there's a good velocity here. It keeps any sedimentation from settling. So the underflow operations are considered a desirable side effect of operating a gate. You wouldn't want the scour velocity to be too high. For example, if you had soil or clay at the bottom of the canal, then it's possible that your supercritical flow here could be causing scour, especially depending on what kind of jump downstream. Remember, in class on Wednesday, we were talking about how different types of jumps, like an oscillating jump or a strong jump, can have some of their velocity vectors pointed downward towards the bottom of the channel. So an underflow gate with any kind of appreciable velocity is probably going to be armored at the bottom with concrete or asphalt lining, or maybe if it's a rock channel, that would be okay. But we do account for energy losses. And the way that we do is with a discharge coefficient, C sub D. And the discharge coefficient is related to both the coefficient of contraction and also the ratio of the upstream depth to the sum of the downstream and upstream depth combined. So here B is the width of the channel, and W is how high the gate itself is opened. So in the previous figure, depending on which book you're looking at, sometimes the figures will call that Y sub G, the depth of the water at the gate. Our book refers to that as W. So the orifice equation is just basically some representation of the area. So B times W is the area that the water is flowing through. And then square root of 2GY1 gives us basically the velocity of the flow from under the gate. And then the coefficient of discharge corrects for energy losses. And that will apply for if it's a radial gate or a flat gate, either one. So let's practice that. Let's use these equations. Let's say we've got a canal here that is 4.3 meters wide, but the gate isn't the full width of the canal. So here, this is telling us that the gate itself is 1.5 meters wide. And the gate is open 45 centimeters, and so that's W, 45 centimeters. And then we know that the upstream depth, Y1, is 2.7 meters. So after contracting, Y2 is 27.5 centimeters. So what's the flow rate through the gate? We want to know what is Q when B is 1.5 meters, when W is 0.45 meters, when Y2 after contraction is 0.275 meters, and let's see, what else do we not know? Well, G would be 9.81 meters per second squared. You're going to have to calculate C sub C. So C sub C is defined as Y2, the depth after contraction, divided by W. And we know Y2 and W. So I'll pause for a moment, calculate C sub C, then calculate C sub D, and then put it into this gate flow equation to predict what is the flow rate in this scenario. Okay, so we've got this gate. We need to calculate the coefficient of contraction because we're going to use that in the discharge coefficient. And the purpose of the discharge coefficient is to account for energy losses as the water goes under the gate. So the coefficient of contraction is 0.6111. Putting that into the discharge coefficient equation, C sub D is 0.5822. And now all of that into the gate equation, where B is the width of the gate, not the channel width necessarily. This is, I guess, a contracted gate, we could call it. So the gate width is not as wide as the channel. So the flow rate, 2.86 cubic meters per second. Now remember that these are not intended for determining the flow. So more typically, what you'd be doing is you'd be given a flow rate Q, and you're asked to determine how is the gate going to perform for a certain flow rate. So you'd be auditioning a gate to see if it's appropriate for the conditions that you've got. You know, for a certain flow rate and discharge coefficient, you'd find out how big is the water going to be pooling upstream. You know, what if you open the gate, for example, a certain height, what kind of pooling is that going to cause? And maybe it's going to overflow the banks of the canal potentially if there's too much pooling. So I just wanted to make the point that, remember, these gates are for flow regulation, not for flow quantification. So usually Q would be a given rather than an unknown. Any questions about that example? So I guess one of the things we could have done in the lab is I could have been playing around with the gate to show you how the opening and closing the gate changes where the hydraulic jump occurs. It happens for the same reason that changing the slope does. When I changed the slope of the flume and it made the jump run away, the jump ran away from me when I made it steeper so that the upstream depth Y1 was less. So the same thing is true when you're causing supercritical flow because the gate is closing. Like if I closed this gate more and brought Y1 down more, then it would push the jump further away from the gate. So sometimes you want to know how much can you open the gate without drowning the hydraulic jump. So the process there is to find out what is the downstream depth in the channel based on Manning's equation. So let's say we know how wide the channel is, we know what it's made out of, the slope. So we use Manning's equation to find out for a certain flow rate what is going to be the downstream depth. Let's call that Y2. So you'd compare it to the critical depth and determine, is this slope mild or steep? And if it's mild, then that means it's going to support a hydraulic jump if you have super going to subcritical flow. The maximum gate opening that you could open this is going to be Y1 divided by the coefficient of contraction. So if you open the gate more than that, then instead of running away, then the hydraulic jump is actually going to come towards the gate, and when it does, then the tailwater is drowning the hydraulic jump. So what we would do is we would have to find the Y1, and this equation is not the same equation I've showed you before. This is the Bellinger momentum equation, yes, but this one is expressed in terms of Y1 on the left-hand side of the equation. And what I showed you before was the Bellinger momentum equation solved for Y2 on the left-hand side. So here, if what we're trying to do is find out how big can we open the gate, we don't want to open the gate so much that the hydraulic jump is coming towards the gate and it's drowned. Then we want Y1 to be the unknown, because Y1 is going to tell us how large we can open the gate W if we divide it by the coefficient of contraction. So the deal is you'll find some maximum gate opening, and if you close the gate more than that, the jump runs away from you, which is fine. If you don't want the jump to be drowned, then it's okay if it's further away than this ideal case. But if you open the gate more, then the jump would be drowned. So remember, we talked about the curves, the rating curve of the tailwater and the rating curve of the jump. And ideally, they're on top of each other. Those two curves are the same. And that would dictate how much you can open up the gate. So here's our second example for the gate. And in this one, this is helping us to figure out how much we can open the gate without drowning the hydraulic jump. So stepping through the process of finding out what's the maximum gate height, and then also what would be Y1. Because we've only got 5 minutes left, I think what we'll do is look at this together rather than me having you do the calculations yourself. So the steps that the solution is going to go through is, first of all, calculating the normal depth downstream. So here, that's called Y after the jump. So we use Manning's equation just to find out for a channel that is 5 meters wide, and if it's carrying 25 cubic meters per second, and then here at the top it tells us the channel slope is 0.3%, the end value is 0.02, and we already knew it was carrying 25 cubic meters per second. So we'll use Manning's equation to find the depth after the jump when it's flowing at the normal depth. So here in this gate example, number 2, we start off calculating what would be the normal depth just based on Manning's equation. So 1.76 meters. So that normal depth, we're going to say that would be the jump, that would be the Y2 after the hydraulic jump. So Y after is what we want to use to find now Y before. So this is the Bellinger momentum equation solving for, here it showed it as Y1 before the jump. Here I've just, because 1 means, Y1 is how our figure is calling the depth upstream of the gate. So there's all these different depths. There's the depth upstream of the gate, there's the depth under the gate, there's the depth after the contraction, then there's the depth after the jump, which we've said here is equal to the normal depth. So we just found out from Manning's equation the normal depth is 1.78. Next, we would find the critical depth just to make sure that we have a mild slope. So I found the flow per unit width, calculated that Our critical depth is 1.366 meters, and that is less than the normal depth. So it is subcritical conditions. A jump will be supported. So we did that component of it. Now let's find y before. And we're going to use the critical depth as one part of finding y before. So this rearrangement of the Bellinger momentum equation allowed me to know that the y, the depth before the jump, is 1.022 meters. Because I had the y after, here I've got the critical depth and so on. So that is the depth before the jump. Now I want to find out the coefficient of contraction, because in the diagram it specifies that we can use a given CC of 0.6. So if we know that the depth after it contracted is this 1.022, then that means that the gate itself is opened to a depth of 1.703. And then therefore we put that into the gate equation and find out that the depth upstream of the gate would be 1.883. So I'm going to email you this one as well, this solution. I think it's important to take a little bit more time looking at it than unfortunately we've had time for today. So I'd ask you to look over not only this first example, the jump length. I don't consider that very important, but this example is really important. You'll probably have an exam question on the final where I'm asking you about flow under a gate. You'll probably have a gate flow question on the final exam. So I think it will be worth your time to look over the example that I'll email to you here in just a minute. So that's all the time we have for. I'll see you on Monday. Remember that this hydraulic jump assignment number 11 is due in class before class on Monday.
Yeah, I guess if it was.